is Jeric Pineda, and I'm yours, today's presenters. In this topic, we're gonna learn how to determine the absolute age or actual age of the object using the process called. So, what is radioactive dating? Radioactive dating, or also known as radiometric dating, it is a technique which used to date materials such as rocks or fossils in which trace radioactive impurities were selectively incorporated when they were formed. This method compares the abundance of naturally occurring radioactive isotope within the materials to the abundance of its decay product, which form at known constant rate of decay. The use of radiometric dating was first published in 1907 by Bertram Boltwood and is now the principal source of information about the absolute age of rocks and other geological features, including the age of fossilized life forms or the age of Earth itself, and can also be used to date a wide range of natural and man-made materials. Together with the stratigraphic principles, radiometric dating methods are used in geochronology to establish the geologic time scale. Radiometric dating is also used to date archaeological materials, including ancient artifacts. Among the best-known techniques are radiocarbon dating, potassium-argon dating, and uranium-lead dating. By allowing the establishment of geological timescale, it provides a significant source of information about the age of fossils and deduce the rates of evolutionary change. Different methods of radiometric dating vary in the timescales over which they are accurate and the materials to which they can be applied. Let's say you have found a fossils and you want to know exactly how long ago these creatures died. So let's come up in a simple chemistry idea. In this topic, it has a little bit chemistry because it has an element an atom contains. We know that all atoms have subatomic particles. It has proton which has positive charge, electrons which has negative charge, and neutron has neutral. If you look back in the periodic table of elements, you found in the top left corner the atomic number of elements. We know that this atomic number tells the number of protons in the element. The truth about this is the number of protons is fixed or it never be changed. For example, hydrogen has atomic number of 1 which has 1 protons, carbon has 6, oxygen has 8, and iron has 26. While the number of protons in an atom is fixed, the number of neutrons is not. Here are the 3 different types of hydrogen. They all have 1 protons because hydrogen has to have 1 proton. If you don't have noticed, these have different number of neutrons. In first, there has no presence of neutrons. And second, it has only 1 neutron. And in the last, it has 2 neutrons. The different varieties of an elements are called isotopes. Take a look at another one, let's say carbon. We know carbon has always 6 protons. Sometimes it will have 6 neutrons also. But carbon has another isotopes or other variety in which carbon has 8 neutrons. It's still a carbon. It's just a different variety or isotopes of carbon. Now the thing is, if the atom has equal number of protons and neutrons, it is stable. But when an atom has an equal number of protons and neutrons, it is radioactive or unstable and begins to break apart in the process called radioactive decay. Here is a picture of process. It is a radioactive atom. If this atom wants to become stable, it will decay, with something to become stable. During this process, it will release energy or nuclear energy. It is an energy that produced in nuclear power plant. For example, carbon-14 is unstable or radioactive. It will decay into nitrogen-14, which is stable. Here's another one example. Uranium-238, which is radioactive or unstable, that will decay in lead-206, which is stable. As I mentioned, carbon-14 and uranium-238 can be called as parent materials, while nitrogen-14 and lead-206 is the daughter materials. Here is the data of radioactive decay. As you can see, there has 4 radioactive isotopes, which is carbon-14, potassium-40, uranium-238, and rubidium-87. And also, show which element disintegrate or decay, and the half-life or accurate year of the process. Let's talk about the half-life. When an atoms of an isotopes decay, they do so at certain rate. The time required for half-life on the atoms in an element to decay is called half-life. For example, let's say the animal just died, and this animal has carbon-14 on it. The moment that it's died, all carbon-14 are still there. 100% of it are still there. Nothing is decayed yet. But after one half-life, it reduced 50% of carbon-14. It has remaining 50%, but if you add them up, it's still 100%. But if we come up in second half-life, another half of carbon-14 will decay. So the parent material has still 25% of carbon-14, and the daughter materials have 75%. After the third half-life, another half of the parent's material will decay, so it became 12.5% of carbon-14. The rest will decay into the daughter materials. And we keep going in fourth half-life, fifth half-life, sixth half-life, and so on and so forth, until we're just taking the half of parent material. When we graph this process, in zero half-life, it has still 100%. But after first half-life, it goes down into 50%. After second half-life, it became 25%. In the third half-life, it will drop down to 12.5%. And so on and so forth. Now, if you're thinking this through, you're gonna realize by taking half, we can reach zero. So the parent materials cannot completely decay, and the daughter materials never reach the 100%. The unique idea about radioactive isotopes is each radioactive isotope has its own half-life. For example, carbon-14 has 5,700 years, and the potassium-40 has 1.3 billion years of half-life to decay, and uranium-238 is 4.5 billion years, and rubidium-87, 49 billion years is a huge amount of time to decay. What's key about this half-life? Its half-life never ever change. Let's look at some practice question. Okay, question number 1. An ancient bone was analyzed and found to contain carbon-14 that had decayed for nearly 2 half-lives. Approximately, how old is the bone? Okay, well, we know that one half-life of carbon-14 is 5,700 years. So, if it's guaranteed in 2 half-lives, it means the 5,700 years went to 2 times. Well, if we multiply the 5,700 years in 2 half-lives, we get the 11,400 years, approximately the age of bone. So let's get the another one. An igneous rock contains 1/2 of its original amount of potassium-40. How old is the rock? Okay, This question telling us that rock contains one half of what is originally it have. So let's back in the chart that discussed before. These charts help you in many reasons in terms of solving radioactive dating question. So the rocks is 50% of potassium 40. If we come up in its original amount, we get 100%. But after one half-life, it reduces in 50%. So the rocks has one half-life. And if we find it in this data, we get 1.3 billion years of one half-life of potassium 40. That more probably the age of rocks. Okay, let's do the last practice question. A sample of wood found in an ancient tomb contains 25% of its original carbon-14. What is the approximate age of this wood sample? So let's come up in this chart again. Well, the wood has remaining 25% of carbon-14. And if we base the 25% in this chart, the 25% is 2 half-lives. So if we multiply 5,700 years into 2 half-lives, we can get the age of wood. And some other things you must consider in radioactive dating. First of all, if you want to use this technique, you want to figure out which element to use. If an element has a short half-life, it decays relatively quickly, so it can only be used to date young objects. For example, carbon-14 can only be used to date things up to 70,000 years old. If you date objects or elements that exceed in 70,000 years old, carbon-14 is not available. If an element has a long half-life, it decays relatively slowly, so it can only be used to date very old objects. For example, uranium-238 can only be used to date things that are more than 4.5 billion years old. And another things you must consider is the abundance of elements in the object. For example, carbon-14 is found in all living things but not in rocks. So if you try to date the rocks, carbon-14 is not acceptable. Same thing in uranium-238. Uranium-238 is found in rocks but not in living things. So if you try to date the living things, uranium-238 is also not acceptable. And that's all. Thank you for listening and watching. I hope you learned in this topic. Thank you.